like accessible and easy to use modeling tools after my talk and also before. And now, or during the IP workshop, the idea came into the world to provide like corresponding Jupyter notebooks based on SimPEG to make IP modeling more available. Because I used the COMSOL multiphysics modeling package, and that's definitely not accessible for everybody in the community because it's quite expensive, right? So when Seogi contacted me and we were looking for like the first step to do, we decided to start with a very simple case. So the simplest case I presented in Newark is the Maxwell-Wagner polarization around a spherical grain immersed in an electrolyte solution. And yeah, although it's maybe the simplest problem, there is like still many ideas to discuss about before maybe the SimPEG community can start to put it into work in the SimPEG environment. So I understand that on your side there is an interest to step into this IP modeling on the Bohr scale, because I know that I won't have the time from now, I don't know, in a year to start diving so deep into the SimPEG package to do it, right? I've already got my COMSOL environment and a license available here at the university, so it's much easier for me to run into this direction and just use COMSOL. And so the step back is to focus on Maxwell-Wagner polarization only, but the step forward would be to put it into work.
Mm-hmm. Yeah, that sounds great. Oh.
In SimPEG.
Oh. Can you hear us?
Yeah, I can hear you.
Okay. Yeah, that sounds good.
It's okay? Okay, perfect. So, and for today, I don't really have a talk, but I thought that some slides and something written down would be much better than just talking about abstract things, right?
Yeah, absolutely. One quick question, Matthias, where are you based?
Yes, of course. Okay, I'm in Germany now.
Okay.
We definitely know that.
Yeah. Okay, Lindsay, Doug and I, we met in Mexico the last time.
Yeah. And
since June, I'm in Germany with my family.
Okay, wonderful.
In Braunschweig. It's a small town close to Hanover, not so far from Berlin.
Okay, nice.
Just in the center of Germany.
Excellent.
Yeah. And it's already dark outside now. So for me, that's the last action today, and then I go home and have dinner and go to bed.
Fair enough.
Okay, so I will try to share my screen.
All right.
Screen share. Does that work?
Yes, it does.
Okay, perfect. So I want to give you like an overview over how to model Maxwell-Wagner polarization around a dielectric and non-conducting sphere immersed in an electrolyte solution. And here goes my location. And these slides are for you. So I would like to describe the problem quickly and then talk a bit about the material properties. Equations are very important. Also the geometry and boundary conditions. And I would also, because that might be a good starting point, give you an idea of the finite element mesh I'm using in COMSOL. And then maybe even a bit more quicker, some thoughts about possible analysis and post-processing steps.
That sounds good.
Okay, so the problem is that standard Maxwell-Wagner polarization only involves materials with homogeneous conductivities. So here, do you see my mouse?
Yes.
Okay, perfect. So here we have a particle with a zero conductivity immersed in a conductive or conducting medium. And if we apply an external electrical field, in the end we will observe this shape of the electrical field with the field lines which are expelled from the particle and the corresponding equipotential lines here in white. So I assume that this problem setup is just what you are doing in SimPEG for DC problems, just on a larger scale. Sorry.
Yeah.
Right?
Yes, that's correct.
Okay, so this would be no problem to model with SimPEG right away.
Mm-hmm.
In this case, this distribution of field lines is caused by a surface charge, which builds up here on the surface of the particle. And this is a true surface charge, and true surface charge for me is a surface charge which does not have a geometrical extension perpendicular to the particle. So it is located on a layer with zero thickness around the surface, right? Okay, but now the problem is that for induced polarization, or at least for most induced polarization mechanisms on the Poor scale, we need particles immersed in an electrolyte. And the electrolyte has the property that it does not permit the charges to accumulate directly on the particle surface or the interface. Due to diffuse fluxes within the electrolyte, the surface charges smear out into the electrolyte. So that's the main problem, maybe, or yeah, the main problem to describe in SimPEG or any other finite element package. Right?
Yeah.
Any questions so far?
I think we have questions, but we haven't quite formulated them yet. So
Okay.
feel free to keep going.
So I will just go on.
Yeah.
So my objectives also always are two. Firstly, see what happens on the micro scale, the micro scale. So visualize the geometry of these diffuse charge clouds, because they can tell us about the physics of the problem, or how the things configure, and give us a better feeling about what happens on the micro scale. So that's one issue or one objective, and the other objectives, the other objective would be to predict the response of this sphere together with the surrounding electrolyte. So we would be interested in an effective conductivity of this compound material, particle or particles in an electrolyte solution, because this would be our medium on the micro or millimeter scale, right?
So Matthias, I unfortunately have to leave, but I want to thank you for joining, and I'm looking forward to picking this up. Lindsay's got it taped, so I can pick it up later. And
okay,
again,
very cool.
We look forward to interacting with you.
Yeah.
Cheers.
I too. Me too. Enjoy the ceremony.
Oh, it should be fun. So thanks a lot. Bye, Matthias.
Bye. Okay, so that's the problem. Now let's talk about the material properties. The spherical particle could, for example, be a silica grain, and the silica grains have a permittivity or relative permittivity of about 4 to 5. And I've already said that we are interested in non-conducting particles. So these sand grains are essentially non-conducting. So this part is easy. And now the electrolyte, the relative permittivity of the electrolyte is high due to the water, or the dipole moment of the water molecules. This is normally assumed to be 80. And we have a problem due to the field-induced diffuse layers, that the ion concentrations are not equal throughout the electrolyte. And that makes the conductivity a function of the, what is it? Of X, of space, right?
So then when you're modeling that, is the conductivity then actually like coupled to the response?
Right, it is coupled to the response.
Okay.
And how it is coupled, I will show that on the next slide.
Okay, cool.
So what is fixed and describes the properties of the electrolyte is what comes down here. That's the bulk ion concentrations. Sorry, there's a mistake. That's not conductivities, that's concentrations. So if I go far away from the particle, the ion concentrations do not vary. So there I can observe the bulk ion concentrations for anions and for cations and for anions. And beside the concentrations, we also have the ion mobilities for the cations and the anions. Like these 4 parameters are fixed for a certain electrolyte. Now, like on this slide.
So Matthias, just got a question. So ion mobility for cations and anions are same?
Okay, that's a simplification in our models. Every cation, every anion has its own mobility.
Okay, I see.
Right? And they can vary, like maybe by a factor 10 or something, but they will always be more or less in this order of magnitude.
I see. Gotcha.
Yeah. So for the sake of simplification, we normally use equal or the same mobilities for both ion species. That's also motivated by the fact that the analytical models we would like to use to compare our numerical results with normally need this simplification to yield an analytical result. So we are still working very close to the analytical models. But one of the ideas for the future modeling with the numerical approaches is to drop this limitation. Okay?
Drop what, Matthias?
Drop
This limitation.
Oh, I see.
Okay.
Yeah, so to consider different mobilities and maybe even more complex electrolyte compositions, like not only one species of cations and one of anions, but like the whole zoo of ions. Right?
Yep.
Cool.
But that's these problems are only accessible with numerical models.
Yeah.
So maybe go ahead to the equations. So within the particle, the conductivity and also the permittivity is constant. That's why the electrical field does not cause any charges to build up. And that's why we can use the Laplace equation to describe the electrical potential within the particle. For the sake of completeness, there are no ion concentrations in or within the particle. So the physics inside the particle are quite simple.
Mm-hmm.
Right? They are described here by this Laplace equation. Now, the interesting part are the equations in the electrolyte. And here we want the ions to move or to be moved by diffuse forces or diffuse fluxes. That's this first term here on the left, on the right-hand side. These are the ion diffusivities, sorry, which can be calculated from the ion mobilities. This is Boltzmann's constant, absolute temperature, and the unit charge. And here we have the gradient of the ion concentrations. So they will move in concentration gradients. That's the diffuse part. And the second term describes the migration of the ions in the electrical field, where we have the mobilities, concentrations, and the gradient of the electrical potential. And we have one of these equations for each ion species. So 2 in the simplest case, and a number of equations for more complex electrolytes. Right?
Yeah.
Okay, and all these ion concentrations are coupled to the electrical potential via this Poisson equation, right? Where this part simply is the charge density,
Yeah.
right? Cation concentrations minus anion concentrations multiplied by the Faraday constant, if the space charge or the charge. And here we have the permittivity of the electrolyte.
Right.
Okay?
Yep.
That's the idea of how the physics works in the electrolyte. Now I will do some manipulations with these equations to get the final equations we want to implement in either COMSOL or SimPEG.
Mm-hmm.
So first, I would like to use this continuity equation, or continuity equations for each ion species. Put this into this equation and get this one.
So
now we see.
Matthias,
Yeah.
in the right-hand side, is that the divergence or a gradient? Like it seems like there's a gradient of J is equal the continuity equation, because
Yeah, sorry, that's the divergence, of course.
I see. So okay.
That's also here. Yeah.
Oh, I see.
I was not very precise here. Sorry. Yeah, that's the divergence.
But then the first ion concentration, that's gradient, right?
Yeah. Ion concentration. So these are gradients, and this is the divergence.
Yeah.
Also here.
Okay. Good.
Okay, so just put this J into here, and we obtain this equation. And then we go to frequency domain and describe the ion concentrations by their bulk concentrations plus a frequency dependent perturbation concentration, which will be a function of space and the frequency of the external excitation, right?
Yeah, got it.
Okay, in the case of the concentrations, we have this static part, which doesn't change. And if we look at the electrical potentials, the electrical potential in the unexcited state is 0. So in the case of the potential is equal to the perturbation.
Matthias, can you repeat what was 0 there? I wasn't quite getting it.
Okay. You see that here we have this perturbation term and this constant term.
Right.
That was just to say that we don't have a constant term here in the case of the electrical potential. We could take one, but we just put it equal to 0.
Hold on. So
you just don't have like a static potential.
Right. There is no static potential.
In the outside.
Everywhere.
Everywhere.
Actually, there's also no static potential inside the particle.
Okay. Okay. So I'll ask it again later.
Yeah.
That's fine. Okay.
Okay. So if we now put these definitions of the concentrations and the potential into this equation, we get this one. If we drop small terms where we have products of 2 perturbation quantities.
Mm-hmm.
Essentially, we just, in this case, we just drop 1 term.
Yeah.
Okay. So we are left with this final equation where we relate the perturbation concentrations of the ion species with their gradient. Here we only have the bulk concentrations, and here the perturbation field or the gradient of the perturbation potential, right? Okay, so to summarize, we now have the final system of equations. These are just the same as on the last slide, one for the cations and one for the anions. And the frequency-dependent formulation of the Poisson equation. And now,
Matthias, the reason why no static potential is that the ion concentration is same at that like an infinite frequency. Is that the idea?
Yes, right.
Mm-hmm. Is that correct?
Yeah, that's correct.
Yeah, sounds good.
So there's 0 total charge, so there's 0 DC potential. Is that
right?
Okay.
Yes, I think his reference is more like infinity.
Not DC potential.
It's infinity.
But,
so
infinite
potential. Okay.
The
sure.
reference is infinity, not 0.
0. Okay. Fair enough.
Mm-hmm. Right. Okay, and all these perturbation concentrations and potentials are complex and frequency dependent variables or parameters, right?
Right. We got 3 parameters, 3 unknowns here, basically.
Yeah, there are 3 unknowns in the electrolyte.
And these all vary in space and in frequency.
They all vary in space and in frequency.
Okay.
Right.
Good.
Good. Perfect. And as I already said, so within the particle, everything is quite easy because we only have this Laplace equation for the perturbation potential.
Right.
Okay. So the next step is the geometry. And the idea is to model this cylindrical volume, which includes this spherical particle. And because it's much faster, and it's possible, until now I've only modeled this 2D domain, like with using an appropriate coordinate transformation. You can just model it 2D, right? To get this 3D response of this very simple and symmetrical 3D problem.
What, we have the same convention?
Pardon?
Oh, sorry. I was mentioning we have the same convention of X and Y here.
Okay.
For some
Perfect. So no problem with this.
True. Oh, no. Sorry. Go ahead, Matthias.
Okay. So now the important parts here are the particle radius and the size of the modeling domain. So this one is, or the radius of this cylinder is at L, and at least in my models, I always use a length of 2L in this direction. Now on the next slides, I will talk about the boundary conditions on these different boundaries. So left and right boundary and the top boundary. On the left and the right boundary, I define a potential which depends on the external electrical field I want to apply to this model. So this would be E0, and just multiplying the electrical field with the length or half length of the domain gives me the electrical potential on these two faces here.
And that is, here E naught is directed along the X direction?
Right.
Okay.
That makes E directed along X direction.
So that's actually,
okay,
that's a boundary condition on the well,
that's the boundary condition on the electrical potential.
Okay.
And it's important to maybe to mention that this is a harmonically varying potential, right? Because we are in frequency domain.
Right. So Matthias, value of E naught is changing in different frequency? No.
No.
Okay, good.
No, I'm using the same E0 for all frequencies.
Yeah.
And so these are, or E0 is a real number and doesn't vary with anything.
Yeah.
Yeah. Okay, and the boundary condition on the ion concentrations is that at a far distance from the particle, where we are here on these two boundaries, must be equal to the bulk concentration. And I realize this condition by equating the perturbation concentrations with 0. So setting them 0, right?
Okay.
So all perturbation concentrations must be 0 far away from the particle.
Except UA, right? Except the potential of.
Yeah, only the perturbation concentrations, right?
Yep, sounds good.
Okay, and then on the top boundary, I want the perturbation or the perpendicular perturbation electrical field to be 0.
Yeah.
Or the electrical field to be aligned with the x-axis.
Yep, that makes sense.
Right? And I also want no fluxes through this boundary. And of course, later on, we will have to make sure that the boundaries are far enough away from the particle to justify these assumptions. So we have to be sure that there are no perturbations which reach out far into the electrolyte and might make these boundary conditions invalid. Okay?
So in our case, we usually consider the top boundary, like you got two boundary conditions for electrical potential or electric fields and the currents, right? That's usually the same, like for our case, but it seems like it's a little bit different here. So for the second one, how are you actually setting the boundary? So are you using the kind of following equation to set up the boundary?
Which equation?
Like for the top boundary one, there are two equations, right? One for basically electrical field, and the other for the current.
Yeah.
The normal component of the currents.
Right.
So to set up that normal currents to 0, are you using the following equation?
The following?
What do you mean?
So there's a following equation.
Oh,
sorry. Yeah. I don't see this equation because there is a notification of Google Hangouts here.
You should be able to hide that.
Yeah, we're not sure what's to hide.
Right. Yeah.
Yeah, so
Already
that equation. So are you using that equation to set up the boundary condition?
I am using this equation, yeah, to set up the boundary condition. It's the same as we saw before. Like, let me go back here. So it's this sum, which has to be 0 on the boundary.
Oh, I see. I see. So that's like I see. That portion is supposed to be 0 at the boundary. Okay, got it. Yeah.
Okay. So these are the boundary conditions on the left, right, and top boundary. Now we also need some boundary conditions on the solid-liquid interface, where we want the electrical potential to be continuous. And we also want to make sure that ions cannot penetrate the particle. So also on this interface, the ion flux densities or perpendicular ion flux densities have to vanish. Again, a no-flow boundary condition.
Yeah. Got it.
And we have also a boundary condition on the displacement current, which looks like this. And maybe you miss charges here on the right-hand side, but that's essentially the problem, right? That we don't want to have true surface charges, because all the charges are in this diffuse layer in the electrolyte. Okay?
Yeah. I'm just curious. It's like that's basically a normal component of the displacement current is continuous, right?
Sorry, yeah, that's again the perpendicular or normal component. I forgot that.
Okay. Yeah, got it. That sounds
right.
good.
Yeah, thank you. Thank you. Okay. So then the problem description is complete. And I would just like to show you the meshes I am using with COMSOL, which might also be a suitable starting point for your modeling with SimPEG.
Mm-hmm.
So my domain size, L, is normally 10 times the particle radius. And the maximum element size of these elements here in the volume is L divided by 20.
Okay.
And particle sizes, well, in this case, it's 0.1 millimeter. But the idea is to be able to model particle sizes from the sub-micrometer range to the millimeter range. And to have it very flexible. And so I would like to zoom in here where the mesh is denser, because we have to resolve the diffuse layer, which is very small, or very thin. So here I have a very fine grid with a minimum element size of p times a, the particle radius, divided by 400. And then into the volume mesh, or the element size increases rapidly. And on the very boundary, COMSOL allows me to define a quadrangle boundary layer mesh, which is, these elements are very long along the boundary. That's these p times a divided by 400. But in perpendicular direction, the smallest spacing is the Debye length divided by 2. I've written down the Debye length here. And so this is, again, I think all these variables are known.
Mm-hmm.
And the main problem is that the Debye length and the thickness of the diffuse layer, normally, or for normal electrolyte concentrations, is in the range of nanometers. So 10 nanometers, more or less. And irrespectively from how large the particle is. So you can imagine that if you want to model a large particle, you have quite a few scales between what you have to resolve at the particle surface and the size of the total domain you have to model. So yeah, these are some more details about these boundary layer meshes.
That's actually that lambda d is much smaller than your minimum element size. Is that correct?
Of the triangular mesh, yeah, yes.
Okay.
That's like, I don't know how you could manage that in SimPEG, or you already have implemented something like that, but that's very fancy in COMSOL. You just say, okay, this boundary layer needs a very finely resolved mesh in the perpendicular direction, and let it be very large in the tangential direction.
Okay. Yeah.
Right.
Well, the easiest way is actually have lots of cells. It's all a big problem.
Well, if it's cylindrically symmetric, though, we can still get away with lots of cells.
Yeah.
What finite element approach are you using? I'm not an expert, but what I know there's like the Galerkin method, and there's other options. Do you know which one this program uses?
That's a very good question. So I'm also not an expert, and I'm using COMSOL almost like a black box.
Yeah, I may look it up.
I
remember from something that I was doing, there's the Galerkin one, and it tends to recover sort of smoother things. So I guess if you're solving for this perturbation in charges directly, you might be recovering a solution that's smoother than the one that you want.
Okay, I will try to find out what's happening there. So if you don't want to go into much detail with COMSOL, you don't have to. And normally, only if you encounter a problem, you start to go deeper into the detail and see where it is, and maybe help COMSOL to make a better decision. But yeah, with this mesh and the like default or automatically selected solvers, it works quite well in comparison to the analytical solutions. So
just a kind of like an engineering question, how so that's like current version is working, I guess, and how coarse can you go like to have a relative good match with your analytic solutions? Like let's say here you're using 8 layers of like really thin, like not sure like quadrangle boundary. Like how coarse can you like sort of go? Have you tried that?
I haven't really done that very systematic, but I have tried to reduce the number of small quadrangular elements, and that made the solution worse. So I just used this one. Yeah, but if it helps you, like this comparison between the COMSOL solution and your solution, I could do it a bit more systematically, just to like find the causes grid which still gives reasonable results.
Yeah.
Okay. Yep.
The other question I have is, so with respect to this internal boundary layer between the particle and the electrolyte, are you actually imposing boundary conditions there, or do they come out of, like, does that naturally fall out of the set of equations that you're solving? Or, like, do you know what I mean? Do you have to actually go in and change the differential operators?
Yeah, some just fall out. That's right.
Okay. So with respect to this internal boundary layer that you have between the particle and the electrolyte, do you have to impose interface conditions there, or does that naturally come out of the set of equations? Are you still there? Oh, are you still there?
Moving. Oh, I think it.
Try calling back. Hey, Matthias. Oh, let's see. Connecting. Let's try.
Okay. Yeah.
Hey, Matthias, I think we lost you on WhatsApp. I'm just trying to call you back.
Are you calling me? No?
Yeah, I'm trying to. Is it coming through?
No. Maybe I try to call you.
Okay, that sounds good.
Because that worked the last time. So I'm calling you.
You're calling me. Okay, it's not coming through yet.
That's strange.
Okay, I'll try just like quitting WhatsApp and restarting it, and maybe if you do the same, we'll see if that takes care of it. Okay, so I'm back on. Do you want me to try calling you?
Just let me see here. I think I'm having troubles with the connection. Okay, now.
Is that coming through?
Yeah.
Excellent.
Am I back with you? Hi. Hello.
Okay, mine still says it's ringing. Maybe it'll just connect in a second. I don't know. Okay, if not, I'll just get everybody. Oh, no, that didn't work. I can sort of hear you, so if you guys want to just come closer, we can. That should be okay.
I think I'm having problems with my internet connection here. I have to introduce my credits and just let's give it a last try.
Okay, yeah, for sure. Did you understand what I was asking?
Yeah.
Yeah.
I think potentially he may not know.
Okay.
Because I think like it's actually like I'm not sure how console works, but I think okay, like here's boundary and then here's a set of equation that you put it in. I think that's probably
That's how it works. I think I've used it once.
Oh, okay. So I mean,
Long
like,
time
it's
ago.
hard to know. He probably doesn't exactly know where the variables are defined.
That's fair.
But for us to do that, you actually need to define that into internal cells.
Yeah.
So actually, I tried that before.
Oh, okay.
So I think as long as you can find the boundaries,
Yeah.
where the boundaries locations are, so boundary faces and stuff. I mean, it's not that bad.
Yeah.
You could formulate that. Yeah. So, I mean, I've tried a couple of times. So,
Cool.
I think it depends on the elements that you're using, because it could be defined in different parts of each element.
Yeah.
Right. So depending on, so you can solve to like a certain order of accuracy. You could use like the center point, or you could use a point that's like a third of the way down from each side. There's different special points inside the element, and I think you're solving it there.
No, I think if the boundary values you don't need to solve, right? So it's known. So technically, we don't really need to solve, but depends upon how you formulate it. You can still put that in and pretend like we're solving it, but no, we're not really doing it. If you think about that Neumann, for instance, we know that values of the current is supposed to be 0, but we're still solving it.
Yeah, it seems it failed
So, I
again,
mean, there's a
unfortunately.
fix, but,
Are you on an iPhone?
I got a response to them.
No. Okay. Well, we can sort of hear you through the computer. It's not ideal, but like it's not horrendous.
Yeah. Yes. Just go ahead.
We'll
Is it
just-
better if I do it like this?
Yes, that's much better.
Okay, so maybe it's just the microphone of my computer.
Okay.
Which is connected and not the one of the headset.
Yeah, because now we can hear you okay.
Okay, so I will make the effort to to sit like this.
Oh, sorry about that, Matthias.
Oh, sorry for this bad technique here on my side.
Oh, no worries. These things happen.
Okay. So I was just looking here in console. Oh, I would like to look into console. It's on a different computer, so you don't see it. Where I define my boundary conditions. And actually, you are completely right with your assumption that the boundary conditions are not defined as such on this internal boundary, but they fall out from the equations.
Okay, cool.
Yeah, that's how it works for this problem in console. So Selby knows that later on we will be interested in putting charge on this boundary, and there the like actual boundary conditions on this boundary come into the play. But now for this problem there are no boundary conditions defined on this internal.
Okay.
Also, the boundary. Once I wrote down here, sorry for that, are only the physical boundary conditions, which are not defined, but are included in the equations.
Okay.
So, like and like the inner boundary condition is not like really defined.
You don't have to enforce it. It falls out of the equations. So like my understanding, and we'll have to write this down afterwards to get this solidified, but is that by defining sort of the physical properties inside the sphere and outside the sphere, that naturally imposes that boundary condition or that interface condition.
I see. Okay.
For this set of equations.
Okay.
Is that a fair statement, Matthias?
Yeah, right.
Okay. Cool.
Yeah, at least if you define one potential for the whole domain and do not define like an inner potential and an outer potential on every domain, but one potential for the whole domain, right? And one variable that describes all ion concentrations, and then via the material properties get like the differences between two parts of the domain, the particle and the electrolyte.
Okay, I think that makes sense.
Yeah, if you define 0 ion concentrations within the particle, there will not be any flux into the particle.
Right.
And if you define 0, or if you define the two different permittivities within the particle and outside the particle, the integration over this boundary like generates or includes the boundary conditions on the current, right? The displacement current and the electrical current. So maybe that was a bit imprecise here in my presentation. Okay. So that was almost already it. And this is only like a perspective of what we could be interested in to analyze and post-process afterwards. So as I mentioned in the beginning, I always like a lot to have a look on the charges, which could easily be calculated from the perturbation concentrations and visualized around the particle. Here I would like to mention that in this case, the particle is almost of the same size as the Debye length, so that you can see this diffusion charge around the particle. But it's much more descriptive to have a look at these small particles to see. So this would be one interesting output. Of course, you can also have a look at the potential variation in the volume and the ion concentrations, the ion flux densities, and see how the ion fluxes move around the particle. There is a whole lot of things you can like extract from this solution once you have it. And it's also very interesting because you can compare it or try to compare it to lab or field measurements. Is calculate the effective conductivity of the model volume by integrating the fluxes to either the left or the right boundary.
And having these fluxes, we just operation and normalize it by the electrical field and the domain size or length size squared, then get the effective conductivity model. And this was the other part which I showed in Newark, the effective spectra of this modeled volume, including one sphere, or you can also use one sphere and rescale it to higher particle concentrations, as you are normally interested in when you want to compare your modeling results and laboratory measurements on sand columns or something like that. And here I also copied again the reference to the paper by Garcia and co-workers, which I used to verify the output of my numerical model. So in terms of the effective conductivity spectra, you can use the predictions of this analytical model, and these authors also provide the solution for at least the charge distribution around the particle. So you can also check, or you cannot only check the effective behavior of your numerical model, but you can also check in detail and if also the microscale predictions are correct. I shared some MATLAB scripts with Seoni. Don't know if you have had a look, maybe not, but there's I think it would be quite easy to adapt these MATLAB scripts to have it in Python and just plot modeled output and compare it to the analytical solution. So that was it, more or less. So what I prepared today. I don't know if that is a good starting point for you to more questions or start right away.
Yeah, thanks, Matthias. I think this definitely is enough to get us started. I mean, questions naturally always arise once you start getting into some of the details and things like that. But yeah, I think this is plenty to go on, and to get a first pass example up and running. We can start playing around with that. Yeah. In terms of like working together on things, maybe we can set up, we have a GitHub organization called SimPEG Research. And we could set up just a repository there to start playing around on notebooks and things like that. And we can add you to that. So if you don't mind, maybe just send us your GitHub handle, if you're on GitHub.
I'm not on GitHub.
Okay. If you're interested in signing up on GitHub, you certainly can. If not, we'll just send you the link of where this is, and you can sort of keep tabs on what we're up to.
Yeah. Oh, that would be perfect.
Yeah, and then the other thing, we use Slack to communicate quite a bit. I don't know if you've used Slack before.
No, I haven't.
So I can send you a sign up link if you're interested. I mean, we're sort of always on there, so it's a good place to instant message us and ping us, and we can do video calls and things like that through there too. So I can send you a link for how to join that if you're interested.
Yeah, that would be great.
Sagi, did you have something you wanted to say?
Nothing particular. I just like had a quick question about there's a inside the sphere and outside the sphere. Are you solving together, or you're solving the outside of the sphere, then solve the inside, or you're not solving the inside? Like how you actually kind of solve those systems?
Okay, very good question. Next, no, I don't know how COMSOL internally does it.
Okay, I see.
I just set it up as one problem and COMSOL.
Right, but can you get the values out inside the sphere as well?
Yes.
Okay, gotcha.
Yeah.
That sounds enough.
Yeah, I think that's enough for us to start like playing with, and then I'm sure we'll get back to you with some questions on how things are working and maybe some comparisons and things like that to get it up and running.
Okay, perfect. That would be really great. So I have to admit that although I really like the idea of SimPEG and using it more, I've not had so much time to play around with it a lot. But at least I installed Python on my computer.
Excellent.
And then I also already installed SimPEG and used one simple DC forward modeling for Schlumberger soundings.
Oh, excellent. Okay.
So that was my first step using SimPEG.
That sounds pretty fast.
There's one notebook, right, describing this tool.
Yeah.
So, just to say that that I'm also really looking forward to go deeper into this stuff, and yeah, it would be nice to have a interesting collaboration on this IP 4-scale modeling and stuff.
Absolutely. Well, hopefully we can get some IP examples up and running, and we'll rope you in.
Yeah, cool. So thank you very much for your time. I don't know if you have any other open questions or issues.
Any other questions?
Nope.
No?
I think that was good enough to start something.
Yep, sounds good. Well, thanks for your time, Matthias, and thanks for putting this presentation together for us. I'm sure we'll be in touch very soon.
Yeah, perfect. And you are very, very welcome. So, and yeah, any question you have, just send me a mail, and I will try to answer it.
Sounds great.
Will do. Well, you have a good evening.
Or then later on meet you on Slack, right? We'll also try that out.
Excellent.
Yeah, cool. Have a nice day. And
all right. Take care.
Thank you.
Bye.